This is a short chapter to introduce the load and resistance factor design, known as LRFD in geotechnical circles. There are two different ways of looking at a geotechnical design. The first one is the allowable stress design, ASD, also known as working stress design, WSD. This is what we have been doing for decades and is still being used and discussed in textbooks. The load and resistance factor design, LRFD, is relatively new and is increasingly becoming popular worldwide and is slowly finding its way into the textbooks. In ASD, we use one lumped factor of safety to account for all uncertainties in the loadings, soil parameters, and the design methods. In LRFD, separate factors of safety are applied to the loads and soil parameters. We will discuss these in the next few slides. Think of a geotechnical application such as a foundation, retaining wall, embankment, etc. We generally have two concerns, A, stability, and B, deformations. We have to ensure that there is no failure in the soil surrounding the structure, and that the structure does not undergo large deformations that are intolerable. The first is an ultimate limit state, and the second is a serviceability limit state. When looking at stability, we need to ensure there is no failure. This requires the shear strength parameters, cohesion and friction angle. Determining deformations require soil stiffness parameters such as Young's modulus. Let's consider the stability of a square pad footing and see how we can carry out an allowable stress design and load and resistance factor design. The figure shows a square pad footing of width B carrying a column load Q, and hence the pressure applied to the soil Q applied is Q on B squared. When the load is increased from 0 to well beyond the bearing capacity failure, the variation of applied pressure versus settlement is shown here. The ultimate bearing capacity is the pressure at which the bearing capacity failure occurs. We have to see that the applied pressure is well below the ultimate bearing capacity, ensuring adequate safety against bearing capacity failure. The column load is a function of the dead load, live load, etc. which are highly variable. Therefore, the applied pressure takes a probabilistic distribution shown in blue. The ultimate bearing capacity is a function of cohesion, friction angle and unit weight of the soil, which are also highly variable. The figure shows the probability density functions of both the applied pressure and the ultimate bearing capacity. Note that the areas under each of these distributions is 1. In the allowable stress design, we deal with the mean values of the applied pressure and the ultimate bearing capacity, denoted by a bar in the figure. The ratio of the two is the factor of safety F, which is usually taken as 3. This large, lumped factor of safety takes into consideration the variabilities in the loadings, soil parameters and the design method. In the LRFD, we overestimate the applied pressure such that there is only a very slight probability of exceeding this value QAP*. To do this, we increase the dead load, live load, etc. by appropriate load factors greater than 1. We also underestimate the ultimate bearing capacity such that there is only a very slight probability of being less than this value QLT*. To do this, we reduce the strength parameters by multiplying by appropriate resistance factors which are less than 1. For the design to be satisfactory, the overestimated applied pressure QAP* must be less or equal to the underestimated ultimate bearing capacity QLT*. No further factor of safety is required as it is already built in while we select these two values. In the standard LRFD, load is denoted by S and resistance by R. The factored load S** is computed using dead load, live load, wind load, earthquake load, etc. which are multiplied by their appropriate load factors greater than 1. The factored resistance R** is computed from the analytical expressions, using reduced values of cohesion, friction angle, etc. Here, we multiply by the resistance factors which are less than 1. The design is satisfactory when S** is less or equal to R**.